Let's write the rate law for the reaction between ammonium ions and nitrite ions. We had the same reaction in an earlier problem, just different set of data. So we can write the rate law as the rate equals the rate constant K times the concentration of one of the reactants. Let's use nitrite, raised to some power. Let's call that X. And the other reactant is ammonium, raised to some power. Let's call that Y. So let's use this initial rates data to find the orders, which is X and Y, with respect to each of these reactants. So let's find the order in nitrite by comparing two trials. So let's label these 1 through 8. So which two trials do we have a concentration change? Well, there's a lot of options here. So we want to pick one where these numbers, these concentrations, are increasing by factors of whole numbers. So we first want to pick two trials where the concentration of the nitrite ion is changing, but not the concentration of the other reactant, ammonium. So let's just pick 1 and 2. Between trials 1 and 2, we can see that the nitrite concentration is doubled. And there is no change in the concentration of the ammonium ion. Now, what did that do to the rate? By doubling the concentration of the nitrite ion, we doubled the rate. I just copied our rate law, so I have a little more room. By doubling the nitrite concentration, we doubled the rate. So to find X, which is the power, you got to ask yourself, 2 raised to what power is equal to 2? And so X is equal to 1. So this reaction is first order in nitrite. We don't write ones, but I'm going to leave that there because it tells you what the order is a little more intentionally. Now let's do the same thing for the ammonium ion concentration. For the ammonium ion concentration, you want to pick two trials where the ammonium ion concentration changes, but not the nitrite. And you want to pick two trials where they go into each other a whole number of times to make the calculations easier. I'm going to pick 6 and 8 because in 6 and 8 you can clearly see the concentration has doubled and the concentration of the nitrite ion is the same. So how did that change the rate? Did it affect it at all? So it doubled the rate. So 2 raised to what power will give you 2? Just like previously, it's going to be 1. So this is also first order in ammonium. So there's our rate law. Now we can solve for the rate constant K. We can pick any one of these trials and plug the data from that experiment directly into this rate law. So let's just pick the first trial. So before we do that, let's rearrange the rate law algebraically to solve for K. So dividing both sides by the concentrations of the reactants, we get K is equal to the rate over the concentration of the nitrite anion raised to the first power times the concentration of the ammonium ion raised to the first power. Now we can just plug the numbers in. Using trial 1, the rate is 5.4 times 10 to the negative 7. And the unit is moles per liter second, or we can write molar times second to negative 1. Now the concentration of the nitrite in trial 1 is 0.01 moles per liter, or 0.01 molar. And we raise that to the first power, and it's going to be what it is. The concentration of the ammonium ion is 0.2. Let me add the sig figs there. I think it was 0.20. Nope, 0.200. So I'm just noticing, depending on which trial you use, you're going to have different sig figs in your answer. All right, let's punch these numbers in our calculator. 5.4 times 10 to the negative 7 divided by 0.01 divided by 0.2. So our answer is 2.7 times 10 to the negative 4. Now one of these molars cancels out, and so the units we're left with is molarity to the negative 1 times seconds to the negative 1. So there's our value for the rate constant K. By the way, you can also rewrite this with units of moles and liters. And since molarity is moles per liter, you'll have units of liters over moles times seconds. So that's probably another common way to see these units. So we can write the final rate law as the rate is equal to 2.7 times 10 to the negative 4 liters over moles times second times the concentration of the nitrite ion raised to the first power times the concentration of the ammonium ion raised to the first power.